Hello everyone. I'm just going to talk a little bit about two theorems dealing with inscribed polygons. One of them dealing with triangles and then the other one with quadrilaterals. And then we'll use each of those in an example. Okay, so when I talk about an inscribed polygon, what I'm talking about is a shape where all the vertices are on a circle. Okay. So for example, an inscribed triangle, all three vertices that make up my triangle would be somewhere on the circle. We have two special theorems that deal with shapes like this. One of them deals with right triangles, and the other one deals with quadrilaterals. So the first one is the Inscribed Right Angle Theorem. And what this one talks about is if we have a triangle inside of a circle and one of the sides is a diameter, then it has to be a right triangle. So let me draw a triangle. So one of the things is we need to have one of these sides be a diameter. So let's say that this is AB. So AB is a diameter of our circle. Okay. Now if that is one of the sides of my triangle, it's going to end up being a right triangle. So if I can pick out just any other point here. So let's say that this is C. And if I connect all this together to make a triangle, so if I got side AC, and if we draw inside BC, this triangle is a right triangle. Okay, so then this angle, angle C, has to be right. The reason this works out, this is just directly follows from the inscribed angle theorem that we've already talked about. So we know that the inscribed angle is half as big as the intercepted arc. So this angle, BCA, this is our inscribed angle. And then the arc is the arc from A all the way around to B. Okay? And because we said that AB has to be diameter, this arc has to be 180 degrees. And then if that arc is 180, that means that the inscribed angle is half as big. So this is half of 180, so this has to be 90. And that works with, any diameter. Point C, I can move this around in a bunch of different places. If we put point C over here, this would still have to be a right triangle. So I'm changing what the triangle looks like. I'm moving point C, but the side lengths are adjusting accordingly, and that is still a right triangle. Right? No matter where we put that point, it's going to be a right triangle. Okay, the second theorem, as I said, it deals with quadrilaterals. So the Inscribed Quadrilateral Theorem. Okay. So what this deals with is if we have an inscribed quadrilateral, so again, that means we have a four-sided shape where all of the vertices are on the circle. So let me say this is A, B, C, D. And then I'll connect these together. Like so. So we know that A, B, C, and D are on the circle. Okay, now what this theorem states is that this is only possible under certain conditions. What has to happen is the opposite angles, okay, so the two pairs of opposite angles, these have to be supplements to each other. Okay, so let's look at that a little bit here. I'm going to try and color code some things. So we have angle A, right, however big that is. Angle A, if I look at that inscribed angle, that matches up with this arc. So all the way from B to D. Okay, so all the way around there. So that arc, that has a measure of 2A. And now if I take a look at C, there's C, however big that is, that inscribed angle matches up with the arc from B to D going the other direction, like that. And this is half as big as that, so this has a measure of 2C. Okay, now if I combine those two things together, we know that 2A plus 2C, that makes up the entire circle. And the entire circle is 360. And now if I cut that in half, since everything is a factor of 2, that tells me that A plus C has to be 180, which means that those two angles are supplements to each other. And we can do the same thing with our other pair of opposite angles, right? Together, the arcs that match up with those make up the entire circle. So cutting it in half, we also get supplements. So opposite angles are supplements. Okay, so two important theorems dealing with inscribed polygons. Let's use both of these in an example. So just real simple, just want to find the value of each of these variables. Okay, so looking at letter A, okay, we have this segment AB. It's going through the center, so I know that's a diameter, which means that this triangle has to be a right triangle. So that means the measure of angle C has to be 90. So then we have that labeled as 2x has to be 90, dividing by 2, x has to be 45. So in that case, it's all about just recognizing the situation. Okay, I know that AB is a diameter, so I know that this angle has to be 90. And in the second one here, I have an inscribed quadrilateral. So now this is using the second theorem. So this is saying that the opposite angles have to be supplements. So we know that measure of angle D plus the measure of angle F has to be 180. And we also know that the measure of angle E plus the measure of angle G has to be 180. Okay, so the two pairs of opposite angles. So we have Z plus AD is equal to 180. Subtracting AD, that gives us Z is equal to 100. And then here we have E is 120 plus Y. And subtracting the 120, that means Y has to be 60. And that's it. That's just using the theorem. Again, I mean, we could take a look at this in another way as well. If I look at this angle of 80, that goes with this in this arc right here. So the arc from E to G. So the measure of arc, and let's say that's EDG, just so we know where we're going. that arc is twice as big as that inscribed angle. So that's 2 times 80, which is 160. If that's 160, the rest of the circle has to be 360 minus that. So the measure of arc EFG, so from E to F to G, 360 minus 160 is 200. So that means the measure of angle D is half of that, which is 100. So again, we can use our inscribed angle theorem, but we use that to discuss our new theorem about the inscribed quadrilaterals. So the opposite angles have to be supplements.